Now we come to a new topic that is called the linear momentum of a system of particles. We already know that for a particle of mass m and velocity v, the momentum, which is designated by P, is given by m into v. Okay. In addition, we also know that by Newton's second law of motion, we know that F is equal to dp upon dt, right? The rate of change of momentum equals the force. These two things I know, right? Now that is for a single particle, right? Now let there be a system of particles. Let there be a system of particles with masses m1, m2, m3, mn. Okay, so these are the masses of the particles, right? They are the masses of the particles with the velocities v1, v2, vn, right? Okay. Now, what is the individual momentums, right? So does the particles have momentum P1, P2, P3, or I'll say P1 is equal to m1 v1, P2 is equal to m2 v2, P3 is equal to m3 v3, and so on, right? Now momentum, as we see, is a multiplication of a scalar, a positive scalar in this case, with a vector, so that itself is a vector. Now what is the sum total of all the momenta? Okay, the sum total of the momenta of individual particles, will be what? It will be added like a vector, is it not? It is P1 plus P2 plus P3 plus Pn, is it not? Okay, so that is the sum total of the momentum of individual particles, and that I call the sum of the system as a whole. So I designate this as P. Okay, vectors, they sum like vectors, and that is all. Fine. So it is m1 v1 plus m2 v2 plus m3 v3 plus mn vn. Okay. Now in the last class we had seen that m1 v1, what had we done? We had first of all seen what? that our R was M1 R1 plus our M into R was this, no? When I had converted my center of mass thing into the position vector, so all those three equations, different equations, they got clubbed into one, and we got this. And then we had found out the derivative of this, so we had got this is equal to dr1 upon dt plus m2 dr2 upon dt plus m3 dr3 upon dt plus mn drn upon dt. Now what is that equal to? So this is actually m1 v1 and this is m2 v2 and this is m3 v3 plus mn vn, and this became the, okay. Now if you see this, this is what is the right hand side of this. So this becomes actually m into v. Now what does that mean? You just remove your concentration from all those individual particles and focus on only one of the particles at the center of mass, and just see how it is moving, right? And multiply that velocity of the center of mass by the full mass of the system, and that gives you the total momentum for the system. Is it not? So again the system is behaving like what? It is behaving like a one particle. Fine. And that's a big relief. That's a big relief for us.
तो जो मास है वो सेंटर ऑफ मास का मास है पूरे
Center of see, it may be so, it may so happen that the center of mass simply does not have a mass, but the mass that seems to be acting at the center of mass is the sum total of all the masses of the individual particles.
Also, sir, the capital V is V1 plus V2 plus V3 plus Vn.
No,
No.
it's not V1 plus V2 plus V3. No, it is this.
So sum of individual velocities is not equals to does not equal
No,
to the
no.
velocity of the
That's a good thing to be confused about. Yes, it is not that the velocity is sum of the velocities. It is that the momenta is the sum of the momentum. Right? The momentum is the sum of the momenta and never the velocity. See, because had that been the case, somehow if I had divided by m, this should have vanished, and that'll never happen. That will happen only for one particle system.
Or if all the particles
Or
are
if
the
all
same
the
mass.
particles.
No, then also not.
Then also it won't, right?
This is nm, right? Then it becomes nm.
Right.
So
You have an
so
n
they
upon
become
n.
1 upon n, right? So velocity never sums to the total velocity. It is the momentum which sums. So if you have to find the velocity of the particle, you first sum the momentum divided by the total mass, and that's how you will get the velocity of the center of mass, right? Do we get that point? We understand that, okay? So somehow my momentum, the sum of all the momentum is nothing but the total mass of the system multiplied by the velocity of that center of mass, right? By the velocity of the center of mass. So somehow this does what? It converts everything into one. Okay, it converts everything into one particle, right? Correct? Now, I'll try to give you an intuitive feel about it. Suppose you have got a computer, okay, and it is able to track all these particles, okay. It is say through some radar or something. It is able to see where the particles are at every moment, and there is a camera which takes a very high speed photography. Now what can be done, you understand? So if you feed say say data about 20 particles which you are concentrating on, and they have a particular position, so immediately the computer will calculate their center of mass. You understand? On a computer screen, and it can show to you, say by a blinking green dot, where the center of mass is. Just try to think, it'll help you in understanding. Now what happens suddenly after, so every time these are moving particles, right? So and they suddenly change their positions. Say in a microsecond the computer again takes the snapshot and again furiously calculates this, where the center of mass is, correct, and then it again plots it. So the blinking dot would have moved some bit, and this it keeps on doing as the particles are randomly moving. So what happens? It will start giving you a trajectory that the green dot takes. You understand? Now in real time you replay the whole thing. Understand? So after it has maybe done it for say 10 seconds and you replay the whole thing, you will find, say there is some green trajectory for the center of mass, say like that. Actually this thing can actually be very easily done. Okay, that's why I'm asking you to understand it that way. So it is like that, and you know the total mass of the system.
So
20
the whole
particles?
system is made up of those 20 particles.
20 particles. Whole system, I am considering the system to be made up of those 20 particles, and the moment I know this trajectory and see its velocity, so I just forget, you erase it from the computer screen, all those 20 particles, and you just see where this has gone, and that is how your momentum of the whole system goes. Right. This will help us in the next step. Fine. So you understand what I'm trying to say?
Like tracking the position of the center of mass.
And if you are able to see, so for example, you'll be able to now draw tangent here. Okay, you'll be able to draw a tangent here. So at this point of time, if someone asks me the momentum, that will be, I have to do nothing. I have to see this vector v, okay, and multiply it by m. So momentum at all these times, because this is the trajectory, the green is the trajectory of the center of mass. Okay, so the center of mass is going like that, and the computer will be able to give you the magnitude of this velocity at this point of time. It will calculate dr. Okay, so what will it do? Actually speaking, for example, this is the origin, so it will shift it by some minuscule amount. This is r, this is r plus dr. Fine. So this vector, you see, it points in the same direction. It will calculate this. It will see what is that dt, dr, that this dr by dt. So it will give you the velocity, right? So at every point you track its velocity. So that's how it is working, correct? This is how the momentum is getting summed up. Fine. So this is my total momentum. So the total.
Is this the principle of which the radars work?
No, radars work on the principle of reflection. So they are tracking mostly one object. If they are not phase array radars, where they are able to track some 20, okay, it is able to track 20 and engage 12, I think. So your Sukhoi 30 planes, they include those phase array radars, costing you some $20 million for a radar, you know, and these are the radars which are static. They do not have a moving canopy, right? It does not have a moving thing like that, because the plane is already moving and you subject it to another movement. So either the plane topples or maybe the radar breaks, right? And you are traveling at say 7G, 8G kind of forces are there. So it is a perfectly static radar which kind of sends out, don't go into that, it sends out signals of varying phases, and it tracks 20, engages 12. So in one go it can engage and shoot 12 planes, right? and can keep on tracking 20. Okay?
Given that we have multiple missiles that can be launched at
Hmm.
once.
Hmm. Okay, because the missiles also nowadays are kind of guided systems, right? So so it guides it also.
Lock and go.
Hmm. So guided missile systems, right? So fine. So this is the total momentum. The total momentum of a system of particles is equal to the product of the total mass of the system and the velocity of the center of mass. So the total momentum of the system equals the product of the total mass of the system and velocity of the center of mass. Right? That is very, very fundamental. So what happens? I suddenly collapse a multiple particle system into a one particle system. Fine. Now, okay, I erase this. Now let us try to see. Suppose I take and this I call capital P. Fine, it is capital P. Okay. Now, what if I take the ddt of this P? Ddt of this P is nothing but ddt of P1 plus ddt of P2 plus ddt of P3 dot ddt of Pn, right? And what is this?
F1.
This is F1, is it not? This is the total force that is acting on the particle 1. This is the total force that is acting on the particle 2. This is the total force that is acting on particle 3. And this is the total force that is acting on particle n. So that is in fact, and we have already discussed that these forces are actually the external forces. So they are the sum total of that is actually the total external force acting on the system. Vector summed, right? Vectorially added, that gives you the total force acting on the system. Is it not? Now, what does that tell you? Okay. Now, if F external is equal to 0, if F external is equal to 0, what happens? What happens if F external is equal to 0? Then it tells me that dP upon dt is equal to 0. Okay. From, let me name this equation 1 and this equation 2. So dP upon dt is equal to 0. It implies that P is equal to constant. P is constant. Now if you see closely, the equation 2 is actually the Newton's law applied for the whole system of particles, right? So equation 2 is Newton's law. So So dp upon dt is equal to 0 tells me that p is, so what I was trying to say was Newton's law applied for this. So you had seen the trajectory of the particle. So at every moment I knew mv. So one mv I subtract from the other. After all, it's a vectorial subtraction that you already know, is it not? Make the negative of the initial, that is reverse its direction, sum it with the second one, you get dp upon dt, and just looking at that one particle, you are able to, you are aware of all the forces, the net of the forces that are acting on the system. You get the point? Do we get the point? So if I see that the particle is moving like that, the center of mass is moving like that, and its magnitude is not changing with time, I am pretty sure that sum total of all the particles on all the 20 particles, that sums to 0. Just by looking at one particle. I do not have to even bother to look at the others. Okay? And if it changes, maybe, okay, so maybe if it is changing like that, it means obviously a force is acting. What that force is, what is the net force, what is the direction, I am able to know just by looking at the blinking dot of that center of gravity. Center of mass. Center of mass. Don't confuse it with center of gravity. They can become different or they can remain the same. Center of mass. So just by looking at the, or just think, even if you don't know whether what is the amount of force that has been applied, if it has changed trajectory, you know that that there is a net force that is getting applied on the system. You understand? Because without a net force, it will not change its direction, right? Newton's first law of motion. The linear momentum is always no.
That's not the first law.
Inertia of direction.
They call it inertia of direction, but the second thing, the inertia of motion actually takes into account that it tells you that body at rest or in a state of uniform motion. So the moment you say uniform motion, it means the velocity is constant. The moment you say velocity is constant, velocity has two attributes, a magnitude and a direction. So both those attributes have to be a constant. So direction automatically becomes constant because you are talking about velocity and not speed, right? So you understand. So what does it mean? What does it mean? It means that if the external force acting on the net of the external force acting on the system equals 0, then its total momentum remains a constant. Okay? Thus, if there is no external force, acting on the system, the total on the system of particles, right? On all the particles, on the system of particles. Hope you understand. All those particles together constitute a system. Many a times you might be led to believe that it might look like a gas where the gaseous particles are flying off, but most of the times it is rigid, right? Most of the times it is rigid. So thus, if there is no external force acting on the system of particles, the momentum of the total momentum of the system remains constant, and this becomes the principle of conservation of momentum for a system of particles. Fine. So this is my principle of conservation of momentum so why not write it here? Principle of conservation of momentum for a system of particles. Okay.
You got the space.
Okay. Fine. So what we had studied earlier for a point object is holding parallelly for the system of particles. Okay, it is holding parallelly for system of particles, and we are fortunate to be having that. Otherwise, the whole thing would have turned on its head, and we would have developed a different physics altogether for a system of particles. Fine. Okay.